corner, we're going to look at common logarithms. Now, we're going to use a calculator today. It doesn't matter if it's scientific or a graphing calculator, but you're going to need one. All right, so when we're talking about common logarithms or common logs, they're a base 10. That's what we're using, base 10. So basically, we're saying that base is always going to be 10. So similar to when we write the variable x, it really is 1x. We just don't write it. It's the same thing when we say log base 10 of x is log of x. We know that that base 10 is there. So we're going to use our calculator to evaluate each expression, and we're going to do it to the nearest 10,000ths. So if you put this in your calculator, you're going to see that the value that comes out is going to be 0.6990. Now, when we're working with our calculator, if you want to pause the video to see what you get, that's fine. In number 2, it is the same thing, right? We said if you don't write a base there, it is assumed a 10. So if you put it in your calculator that way, you're still going to get the same value. All right, and for the last one, we have log of 0.3, and you have negative 0.5229. Okay, moving on. It says we have both sides of an exponential equation. If it can't be easily written as powers to the same base, you can use logs to help solve them. Okay, so in number 4, for instance, I can't do anything. I can't get 4 and 19 to work within the same base, so I can use logs to help me. Okay, so I can say log 4 to the x power. Now, again, we're assuming, right, that that's a base 10 there. We're just not going to write it. And then we have log of 19. Now, I'm following the properties we've learned in the previous lessons that x goes out front. So I have x times log of 4 is equal log of 19. Now, I want to get that x by itself. So I'm going to divide both sides by log of 4. And I have x is equal to log of 19 divided by log of 4. Now, when you put those values in your calculator, you end up with x is equal to 2.1240. All right, the next problem, we have an inequality sign. All the rules are going to be the same, whether you're using an inequality sign or an equal sign. So let's see what we have. So I have log of 3 to the 5y power is less than log of 7 to the y minus 2 power. Okay, again, I'm going to bring my exponent out front. So I have 5y times log of 3 is less than y minus 2 times log of 7. Okay, I need to distribute that y minus 2 through with that log of 7. So we're going to rewrite the left-hand side, 5y times log of 3 is less than. Now, I'm basically, again, distributing that log of 7. So I have y log of 7 minus 2 log of 7. Now, I need to get my y's by themselves. So I have a y here and a y here. Okay, so similar to just a basic algebra problem. So I'm going to bring this to the other side, this one to the other side. So I have 5y log of 3 minus y log of 7 is equal to negative 2 log of 7. Okay, I still have to isolate that y. So I'm going to have y times 5 log of 3 minus log of 7 is equal to negative 2 log of 7. Okay, almost ready to isolate that y, right? So I'm going to divide both sides by 5 log of 3 minus 5 log of 7. So I have 5 log of 3 minus log of 7. And that's all going to equal to, oh, not equal, sorry, I have to go back. I just had a habit, I put equal sign, so we'll just fix that real quick. That's less than. So in the end, I have y is less than negative 2 log of 7 over 5 log of 3 minus log of 7. Now, this is where you just have to be careful when you put it in your calculator. You can either put it in all at once or just put in the top value, hit equal sign, and then divide your answer by what you have in the denominator. So in the end, I'm going to have y such that y is less than negative 1.0972. All right, moving on. We have one more rule. We're going to change the base of the formula. So this is a little tricky. It's very basic, but I always wondered, like, how do you know that you can do that? So we're going to look at the y in this one, almost like a proof in geometry. So what the formula can do is there is my original formula, right? There's my original log of log base 3 of 11, and I can change that. Again, we're working with log base 10. My bigger number around my argument is going to be the numerator, and my base is going to be the denominator. Now, again, like I said, why can we do that? Well, let's look. Here's the proof of this. Let's look, why can we do that? Okay. Now, remember, this is my base, and my x is my exponent, and my argument's my answer. Okay, now I can change that to my log. I'll say base b, even though that we know that's going to be 10. A to the x is equal to log base b to the n. Okay, now again, I bring that x out front. So I have x times log base b of a is equal to log base b of n. So when we divide both sides by log base b of a, I end up with log base b of n divided by log base b of a. Now, if you look at that, that's exactly what we have up here. Now remember, we started with this, right? So this is really equal to log base a of n, where our base becomes our numerator. I'm sorry, not our base, our argument becomes our numerator, and our base becomes our denominator. Okay, so these problems end up being very basic, but I wanted to really show you why. So this ends up being log of 20 over log of 3. Now, we know that there is a 10 there, but we don't have to write that, right? We talked about that earlier. So it's just log base 20. My argument goes in the top, and then my base is on the bottom. So when I use my calculator, I have 2.7268 for the value of that beginning log. Okay, same thing, one more. So I have log of 8 over log of 6, and that gives me 1.1606 as my final answer. Okay, thanks so much for stopping by today. Have a good day.